Hello everyone and welcome back. In this video, we're going to talk about buoyancy and Archimedes' principle. Hello everyone, we are going to start the study of fluid dynamics, which is the study of fluids that are moving. Some examples that we may encounter during this topic are water flowing through pipes or a garden hose, water flowing in a river or stream, maybe gasoline flowing from the gas pump, wind blowing, or maybe even air moving in a tornado or hurricane. Our first concept is volume flow rate. Volume flow rate is the amount of liquid that passes per unit of time. And volume flow rate in a moving fluid is always constant. So for example, if we had a river that was flowing and one part of the river was wide and another part of the river was narrow, that means the same volume of water has to pass each point at the same time. So if all of this water passes the wide part of the river and the same volume of water has to get through the narrow part of the river, that means that when the path narrows, the velocity of the water is going to have to increase. So that's a fact that always happens with a fluid. When a path narrows, the velocity increases. The equation for volume flow rate equals AV. A stands for the cross-sectional area, and V is the velocity. There is no variable for volume flow rate, so that's why I wrote the word out, and it's a concept. But let's look closely at the units. So volume flow rate means volume per unit of time. So volume is in meters cubed, and time is going to be in seconds. A cross-sectional area, pretend if you had a pipe and you sliced that pipe in half, the open part of the pipe would be a circle. That would be pi r squared. And so the area, or the units for area, would be meters squared, and the units for velocity would be meters per second. And you can see that when you take AV and you multiply it, you will get the units of volume flow rate. The law of continuity allows us to mathematically compare the cross-sectional area and velocity of a moving fluid at any 2 points. So for example, we have a river here that has a narrow section and a wide section. We'll call this point 1 and we'll call this point 2. The volume flow rate is the same. So the volume flow rate, or the area times velocity at point 1, has to equal the area times the velocity at point 2. So we'll look at that in a minute. Before we move on though, quick check. As this river flows from point 1 to point 2, does the river speed up or slow down? Yeah, it slows down because all the water is rushing through point 1, and then when it gets to point 2 where it's wider, the water can slow down to allow the same amount of volume to flow per second. Let's look at an example involving the law of continuity. It says water flows through a pipe. At point 1, the radius of the pipe is 4 meters and the water has a velocity of 3 meters per second. At point 2, the pipe narrows and the radius is 2 meters. What is the velocity of the water at point 2? So the law of continuity allows us to compare 2 points. So I have to identify my points. So I'm going to call this point 1 and I'm going to call this point 2. So we know that the radius is 4 at point 1 and the velocity is 3. At point 2, the pipe narrows and the radius is 2, and we are solving for the velocity. So we can use the law of continuity to compare the volume flow rate at each point. So at point 1, if I took a cross-sectional area, that would be a circle. So pi r squared times the velocity, and point 2, I also have a cross-sectional area. So you can see that the pi will cancel out of both sides. So the radius at point 1 is 4 squared times 3, the radius here, 2 squared times v2. And I can solve for the velocity at point 2. Now, just looking at the pipe, we know that the pipe is narrowing and we would expect the velocity to be speeding up. So the velocity was 3 and now we have a velocity of 12, so that makes sense. In a previous lesson, we learned that pressure decreases with altitude and that it increases with depth. When it increases with depth, the change in pressure is equal to rho GH. Well, we're now going to add on another fact about pressure. So Bernoulli's principle says that pressure decreases with velocity. And Bernoulli's equation is that the change in pressure is going to be equal to 1/2 times rho, meaning the density of the fluid, times the velocity of the fluid. I once had a student who said, so when the wind whips, the pressure dips. And it's been a great memory tool. But I do want to point out that it's not only wind, it also applies to all fluids. Let's look at an example involving pressure and velocity. In this problem, it says, during a windstorm, an 80-mile-an-hour wind gust blows across the flat roof of a small house. Part A says, calculate the pressure difference between the air inside the house and the air outside of the house. So let's look at that. So we're going to make an assumption it's a normal day, meaning that the air pressure inside the house is 101,325, and the air outside the house is 101,325. But now during the windstorm, when this gust of wind comes, the wind is going to pass over the house, and when the wind whips, the pressure is going to dip. So I'm looking for that pressure difference. How much is it going to dip? And we can use Bernoulli's equation to answer that. So the change in pressure is going to be equal to 1/2 times rho b squared. 1/2 rho is the density of the fluid. And this fluid is air, and the density of air is 1.29. The velocity of the air is 35.8 then squared. So we get a pressure difference of 826.66 pascals. That's how much the pressure is going to change. But if the pressure is going to change outside the house, it was 101,325. Now I'm subtracting 826. So now the pressure outside of the house is 100,498 pascals. So now there's a pressure difference between inside the house and outside of the house. Part B says, if a typical roof has an area of 150 meters squared, what upward force acts on the roof? So again, we have this pressure difference happening, and when you have a pressure difference, you can calculate the force. So the change in pressure is going to be equal to the force over area. So again, be very careful here that it's the change in pressure. It's the pressure difference that creates this upward force. And so the area is 150, and that the force acting on the roof is 1.24 times 10 to the 5th newtons. So this pressure difference creates an upward force and can blow the roof off of a house, which is something that's commonly seen in tornadoes or in hurricanes. The same concept also explains the lift force on an airplane. For example, airplane wings are designed so that the top of the wing has a narrower path than the bottom of the wing. And you can see here the air coming can pass easily under the wing, but when it goes above the wing, the path narrows. And when the path narrows, we know that the velocity is going to be faster. So the air is moving faster over the top of the wing, and when the air moves faster, when the wind whips, the pressure dips. So the pressure above the wing is going to be less. I just made up this number. So we have 101,325 below the wing and maybe only 50,000 above the wing. And this change in pressure is going to create an upward lift force. So next time you're on an airplane and you're getting ready to take off and you're going down the runway and you feel that immediate lift, you can say to yourself, that is Bernoulli.